Hello everyone and welcome to the fourth episode of CPP Next. In this episode we will continue exploring the crazy behavior of re-entropcast and how to avoid scary situations in your code by using it correctly. We will talk about not so known function that was introduced in C++17 called launder and how to use it correctly. Let's start by looking at this code. Let's look at the code. The code itself is really simple. We are just creating a struct x with a member y inside it in the size of int. Then we are creating a buffer on the stack. We are calling it buff. It will be of size of x and we will align it to x as well. Then in line number 6 we're using placement new to create a new object in the allocated memory. So this is basically an example of a small and simple memory pool buffering. We know that we have allocated the memory. We don't want to allocate the memory again and again for that object, but we will reuse it because we have the buffer and we can allocate a new object inside the same buffer again and again. In line number 7, we want to take the y member from the buffer. We are using re-entropcast. We are casting the buffer back to x and then we are accessing y. And this is undefined behavior. Although re-entropcast from bytes to x is absolutely fine, accessing the data member is undefined because the compiler may not know that the x object resides inside the memory. It sees the bytes memory, so it can optimize out, it can do whatever it wants. That's why it's called undefined behavior. Luckily for us, C++17 introduced a new function called launder. Launder is basically our answer to this type of usage. Let's fix it with this function. std_launder function is located inside the new header. And all we need to do to fix this from being undefined behavior to an absolutely defined behavior is a very, very simple usage of std_launder. And that's basically it. How does that work? If you would look at CPP reference, we would see that std_launder is a very simple function that receives a pointer of type t, any type, and returns a pointer of the same type. So how does it work? This function has side effects. Because this function has side effects, the compiler cannot assume it can optimize anything. It received a pointer and then it returned a different pointer out. So with taking this into account, basically we're telling the compiler, don't optimize anything. The pointer you are receiving is an actual pointer of the type that we are returning. And it cannot assume anything about it, and it will not optimize anything, and that's why it's not undefined behavior anymore. So the launder function, it's what it's called. It's laundering the memory. It's making the compiler understand that the memory that we are passing to it is the actual memory of the type that we're meaning it is. So in our case, when we use std_launder from the re-entropcast returned a pointer of x. And then we used launder. So launder received a pointer of type x and then returned the same pointer out, but the compiler cannot optimize it out. And we just laundered the memory and made everyone understand that this is a pointer of type x. I hope that now you understand the importance of std_launder and why you should use it in your code. Basically, this is the end of the episode. I just want to note that I will be in Canada this week in CPP North. So if you're in the conference, come say hi and come to my talk about C++ memory modules since C++11 to C++23. I will be given 90 minutes talk this time. Hope to see you there. And as always, like and subscribe and see you in the next episode, everyone.